Okay, hello all you crazy people out there. My name is Michael. I like wizards and dragons and making games. Welcome back to 3D Collisions in GameMaker. So far in Act 2, we've defined some simple things with triangles. We've defined collisions with triangles and spheres. That's pretty easy. We've also talked about the separated axis theorem, which is a tool for helping us to find axes of separation between arbitrary shapes to see if they intersect or not. And today we're going to be writing a few more helper functions, which are going to come in handy in various places in the coming weeks. That shouldn't take too long, and assuming it doesn't, I'll also be getting on to checking for collisions between triangles and axis-aligned bounding boxes, as well as triangles and planes, the latter being somewhat simpler. So the first additional function we're going to implement is going to be a method belonging to the vector3 class. And this is going to be a new method, which I have not really mentioned so far, but it can come in handy, and that is going to be static project. And that is going to be a function which takes an argument of a direction. This is the direction parameter for, come on, help. There we go. The direction parameter for the projection function method, whatever, is going to not be just a degree value or a radian value or anything like that, but it's going to be another vector itself. If we project one vector onto another, we are essentially going to be getting the magnitude of that vector in the direction of the second vector. I'll have a diagram of what I mean on the screen right now. Hopefully it's comprehensible, at least on the standards of linear algebra anyway. So let's start off by saying var dot is going to be the dot product of ourselves, of our own vector, and we're going to dot ourselves against the direction. The magnitude is going to be the magnitude of the direction. And to project our vector onto another, we are simply going to return direction dot multiply the dot product divided by the magnitude squared. As a bit of an aside, I have elected to not do this wherever it might come up, but in some places, for optimization purposes, because it's slightly more efficient to calculate, you might see magnitude squared defined by a vector dot product against itself. And if you recall the way that the dot product works, it's the product of the x components of the two vectors multiplied by the product of the y components of the two vectors multiplied by the products of the two z components. If both vectors are the same, that's basically the value that's under the radical in the distance formula. And you can use that to get the magnitude of a vector squared without having to do a square root, which is... It's one of those things that, yes, it's technically more expensive, but since GML is a very, very slow language anyway, a single square root here and there is probably not going to be where the slowdown in your code comes in, but I just thought it might be worth mentioning that. Anyway, another helper function that I would like to implement is going to be... where is the plane? The plane is just this one. Okay, I'm right here. We are going to implement something similar to the dot product for a plane, and that is going to be... I don't know if this actually has a name. I've just seen it called on the internet and elsewhere the plane equation, which makes it sound like cryptic and arcane, but all this really is it functions a lot like the dot product in that it returns a value between 0 and 1 to describe where a point is in relation to a plane. I'm going to say this is going to be a function, and it's going to take a vec3 as an input. If any of you are interested in astronomy or space travel, you may have heard of something called the rocket equation, and rest assured, the plane equation is quite a bit simpler than the rocket equation. That's an aerospace joke, I'm really sorry. So the plane equation actually functions quite a bit like the dot product in that it will take a vector, a point in space, and compare it to, instead of another vector, we'll compare it to a plane, and the plane equation will return a value of +1, or positive something anyway, if the vector is in front of the plane. It will return a value of 0 if the vector lies on the plane, and it will return a value of something negative if the vector is behind the plane. Again, that's like the dot product. If the point lies on the plane, then its plane equation value is going to be 0. If the point lies in front of the plane, then its plane equation value is going to be some positive number. It's going to be 1 or so. And if the point lies behind the plane in the opposite direction of the plane's normal, then its plane equation value is going to be -1. You can probably imagine how this is going to work as well. In fact, if we start with the dot product, we can say var dot is going to equal vec3 dot dot against self dot normal. We're going to be taking the dot product of that vector against the plane's normal, and we're simply going to return dot minus self dot distance. So we're going to take the relation between the vector and the plane's normal, and we're going to subtract out the plane's distance from the origin, and that is going to give us the plane equation value. So again, that's a lot like the dot product, the regular dot product. I guess I might as well, this is something I might leave a comment for. And that's the plane equation. Okay, that is the plane equation. Let us move on to triangles. And we have something called a barycentric coordinate, which is going to be becoming relevant in, I think, several videos from now. And we would like a method which can return a barycentric coordinate of a point in space on a triangle. So barycentric coordinates aren't really something where the name gives away what it does, at least not in an obvious way. So a barycentric coordinate is a way of measuring a point's position relative to the three vertices of a triangle. Let me type out. I guess I'll call this, I'll call this barycentric just to keep things simple. It's going to be a function, and it's going to take a vector 3 as an input. And and the barycentric coordinate is going to be a vector 3 itself, but instead of representing points in space, instead of representing an XYZ position in world space, the three components of the barycentric coordinate are going to measure how close the input vector 3 is to each of the vertices that compose the triangle A, B, and C. For example, if the input vector 3 is located on point A, then its barycentric coordinate is going to be 1, 0, 0. If the input vector 3 is located on point B, then its barycentric coordinate is going to be 0, 1, 0. If the vector 3 is located on point C, it's going to be 0, 0, 1. And if it's in the middle of the triangle, it'll be around about 0.5 on all three axes. If it's outside the triangle, its barycentric coordinate may be greater than 1 or less than 1 or something like that. I'm not going to be making use of this calculation right now in the immediate future, but farther on down the line I will be using it. So let us start by doing something that I did in, I believe, the point triangle calculation, and that is going to be var PA is going to be vec3 dot sub self dot A. Var PB is going to be vec3 dot sub self dot B. Var PC is going to be vec3 dot sub self dot C. And as this was the last time we did something like this, this is going to be transforming each of the coordinates of the triangle into coordinate space relative to the input vector, into the input point. Next, let's turn this into lines. Let us say var AB is going to be self.b.sub self.a. So this is going to be a vector from point B to point A, or from point A to point B, depending on your perspective. It's going to be one of the edges of the triangle. Var AC is going to be self.c.sub. I don't really need the parentheses there. Self.a. We want these going in both directions. Next, we have our, say, BC is going to be self.c.sub self.b. And let's go the other way for two of these vectors. Let's say our CB is going to be equal to self.b.sub self.c, and our lastly CA is going to be self.a.sub self.c. This is going to be 5 values, you may notice. The only one that's really missing, you may observe, is going to be var BA is going to be self.a.sub self.b, but I don't believe we're actually going to need that, so there's no point in calculating a value that we're not going to use, wasting CPU cycles. Next, we've got the edges. We can say var v is going to be equal to ab.sub ab.project cb. This is unfortunately where my ability to describe what's going on here is going to start falling short a little bit. Honestly, I was kind of struggling to think of ways to describe the projection function itself, too. But regardless, when I go to edit this video, I'll try to come up with a way to visually describe what's going on here, because this is definitely a little bit more on the abstract side.
Hey.
Anyway, the value v here is going to represent vector AB projected onto vector CB, so the two sides of the triangle. Next, I'm going to say A is going to equal 1 minus v dot dot against AP, or PA, I'm sorry. And that is going to be, remember, point A relative to the input vector. And we are going to divide by v dot AB. Next, v is going to be redefined as, let me scroll down, bc dot sub bc dot project AC, and we can say var b is going to equal 1 minus, and this is going to look rather similar to the last block of code, v dot pb divided by v dot bc. And we're going to do this one more time. V is going to be redefined again as ca dot sub ca dot project on AB, and var c is going to equal 1 minus v dot pc divided by v dot ca. And here, A, B, and C are going to be our barycentric coordinates. Now all we have to do is return a new vector 3 composed of A, B, and C. And that is our barycentric coordinate. That'll be something that I'll be forgetting about for a couple videos and then coming back to. And then I'm sure by the time we get there, I'll be glad that I did it now and I won't have to do it again in the future. Okay, how long have I been recording? I've been recording for 19 minutes. I have all the pieces in place for axis-aligned bounding box versus triangles and planes versus triangles. Do I want to keep going? How quickly do I think I can get this done is the important question. Okay, you know what? Axis-aligned bounding box and triangle is just going to be a little bit of separating axis theorem, which I shouldn't take too long to explain because that was what the entire last video was about. And planes versus triangle is... Honestly, I think planes versus triangle is a lot of fun. And I've realized how nerdy that sounds, but regardless, we'll do it. So let me make a commit. This is going to be some extra helper functions. And I guess, should I rename this branch? Can I rename this branch? Because it's no longer just going to be the helper functions. It's also going to be, I can rename. Helper functions and AABB and plane. All right. That's what the week 12 branch is going to be named now. So let's do the SAT. In the AABB collision shape in check triangle, first let us define the edges of said triangle. We've seen this before. I'm going to call it var AB is triangle dot B dot sub triangle dot A. Var BC is going to be triangle dot C dot sub triangle dot B, and var CA is going to be triangle dot A dot sub triangle dot C. So these are the three edges. These are the three vectors representing the three edges of these triangles. Next, we are going to have a few our axes. This is going to be var axes is going to be an array. This is going to be a somewhat longer array of axes of potential separation than we had for AABB versus AABB. We're going to have the same ones. We're going to have the same normal vectors that we had for the axis line bounding boxes. So we'll start by saying new vector 3, 1, 0, 0, new vector 3, 0, 1, 0, and a new vector 3, 0, 0, 1. That needs to be a 0 up here. So we have the x, y, and z axes of potential separation. We also have, because triangles are more complicated shapes, which may have more potential axes than just two blocks, we're going to have the surface normal of the triangle. You could potentially draw a line between the triangle and the axis line bounding box on its surface normal. So that's going to be triangle.getNormal. And we also have the cross products of each of these normals, each of the x, y, and z normals against each of the edges of the triangle. And you know what I'm actually going to do is I'm actually going to, instead of typing out the vector 3's representing the axes over and over again, I'm going to define them down here as var nx, var ny, and var nz. To this day, every time I see nx, I think of the Nintendo Switch's code name. And in the axes array, we're going to be saying nx, ny, and nz. And we're not going to be evaluating vectors of these of this exact value every single time. So as I said, the each of these three vectors crossed against each of the three edges of the triangle, so that's going to be 9 more potential axes of separation. So this is going to be a total of 13 items in this array of axes. So we have nx dot cross edge AB. Did I say cross or dot? And I'm just going to call that AB because that's... In my notes, I called it edge AB, but then I decided I don't feel like typing that out over and over again. Anyway, it's going to be nx.crossProduct against AB, nx.crossProduct against BC, and nx.crossProduct against CA. We're going to do this 2 more times for ny, like this, and nz, like this. And this is going to give us 13 axes of separation. And then... much like we did in the SAT version of AABB versus AABB, we are just going to loop over every one of these axes. Where are we? Up here. And instead of saying for I equals 0, I is less than 3, it's going to be I equals 0, I is less than 13, I plus plus. You could just get the length of the axes array if you want, but it's not like that value is ever going to change here. And we are going to do the same overlap test that we did for call underscore overlap underscore axis for, instead of another AABB, it's going to be the triangle. And we will need to implement the getInterval method for triangles. And if I scroll down, I didn't already do that, did I? I don't believe I did. I'm pretty sure I did not already do the interval method for triangles. And it looks like I did not. Okay. So as a bit of a refresher, and let me just collapse all these so I don't have to scroll so far. Check line doesn't matter. Check normal we've already done. Get plane we've already done. Get nearest point we've already done. Barycentric we've already done. The entire plane class I can collapse right now. So as a bit of a refresher, for the axis line bounding box, the way we did getInterval was by figuring out each of the 3 points of the axis line bounding box, looping over that array, and getting the minimum of the dot product between the axis and said vertex. That was definitely what one might call the most efficient way to do that for an axis-aligned bounding box, because the axis-aligned bounding box has 8 points, 8 vertices that you will need to check. Triangles being simpler shapes which only have 3 vertices. We can get away with doing a little bit less work. I'm going to say static getInterval is going to be a function that takes an axis as a parameter. I'm going to call it var I min is going to be the minimum value of, instead of putting all the vertices in a loop and looping over that, putting them in an array rather and looping over the array, I'm going to instead just hard code all these. I'm going to say axis dot dot self dot a, axis dot dot self dot b, and axis dot dot self dot c. The GameMaker's min and max functions can take as many arguments as you want to give them. So you would ordinarily use the min and max functions with just 2 arguments. I'm going to be using the min and max functions with 3 arguments here. If you, for whatever reason, ever needed to do the min and max functions with 4 or 5 or 6 or however many arguments, you should be able to do that. In the book that I've often referenced that I've been using for a lot of my research for this series, Game Physics Cookbook, Gabor Zara, the author, did actually put the 3 vertices of the triangle in a loop, but and I did it again in an array and loop over an array to get the minimum and maximum values, but I personally think that's a little bit overkill. And in any case, since let's just say C code comes with a little bit less overhead on things like loops than GameMaker code does, and since C and C++ give you some fun things like unions, which you can take advantage of for things like this. And GameMaker language does not. I'm just going to be hard coding the minimum and maximum values in the like this. So we have our min and max values, so we can just return a new call interval, I min, I max. And that should allow us to use the separated axis theorem, and check for triangles for collision against axis-aligned bounding boxes. I believe that's all we need to do. Let me run the game, and I hope this doesn't blow up in my face. The way it did when I tried to show something earlier and I didn't have a new in front of a constructor and things got weird. Let's see, I'm going to ask for a triangle. I'm going to ask for an axis-aligned bounding box, and we do not have a collision between the triangle and the axis-aligned bounding box. Am I, Did I forget in the triangle class to reflect the check ab method? I did. So we're going to say return ab.check triangle. Okay. I had a feeling that was the more likely thing to be going wrong. So we're going to have a triangle versus an ab, and if I were to, it's still not working. Now I gotta go hunting for typos. Oh, wow, okay. You are a little laughing right now. At the end of this function, if no separating axis is found, return true. Alright, I was like checking to see if I had like gone cross-eyed writing down A's and B's and C's up here in the body of the function, but nope. I just need to actually return true if no axis of separation is found. Okay, embarrassing code errors all day here. So now we can see that this is indeed working as it should be. The block is overlapping the triangle. If I were to move it out here, the block is no longer overlapping the triangle. If I move it out here, again, left, right, wherever we happen to be, if I were to move it down below the block, we are no longer overlapping. We have an axis of separation that is the basically the x-axis over here. If I were to move it up, same thing. We have an axis of separation. Okay, so that is triangle plane. How long have I been recording today for? This has been going on for 33 minutes. Hopefully that'll be cut down. I know I've spent like 5 minutes checking for typos in the code and not finding any. Next, we're going to do triangles and planes. So first, let me head off one of those embarrassing errors by going into triangles check plane method and turning that on its head. Return plane dot check triangle with ourself. And now we can actually implement triangles and planes. So if I were to go into the, that is the ab class in the plane class, if I were to check the triangle. So figuring out if a triangle intersects a plane is fairly easy. We have the plane equation, which is like the dot products, but for a vector and a plane rather than two vectors. And we can use that to figure out which side of the plane any given point is. And if all of the points of a triangle are on the same side of a plane, then there is no intersection between the plane and the triangle. Otherwise, if some points are on different sides of the plane than others, then that means the triangle has to pass through it at some point. Worth noting, by the way, for planes, I will not be implementing getInterval, because getInterval is kind of useless for planes because planes are infinite. And the plane's interval on any given axis is going to be either 0 if the plane is perpendicular to the axis, or it's going to be infinite because the plane is going to just run off infinitely in all directions. And we won't be using any SAT tests between planes and other shapes. At least I'm pretty sure we won't. I'm going to assume that we won't, because the interval for a plane is somewhat meaningless. Anyway, we can figure out which side of the plane all three points of a triangle are on. So we can say, let's say our side A is going to be self.plane equation of triangle.A. We are going to do this 3 times for points A, B, and C on the triangle. Now, there is a bit of a special edge case here. If the triangle lies completely flat on the plane, then you would consider the triangle to be intersecting the plane, but all three of the plane equations of the 3 points are going to be 0. So we can take care of that early on by saying if side A equals 0 and side B equals 0 and side C equals 0, then we can simply return true. Otherwise, if If each of these points of the triangle are on the same side of the plane, then their plane equation values will have the same sign. They will either be all positive or all negative. If, let's say, sine of side A is equal to sine. I'm getting sine and side mixed up. Psi of side B, and I have a rogue parentheses there. If the sine of side A equals the sine of side. I really hope I never have to say the word sine or side ever again in my life. Side C. I guess I should just be grateful that I don't have to take the sine of the side. Ugh. If all three of the points of the triangle are on the same side of the plane, there is no collision. Return false. Lastly, if the 3 points of the triangle are on different sides of the plane, return true, there is a collision. And that should allow us to have a plane intersect a triangle. I am going to generate a triangle. I am going to, let's say, generate a plane. The shapes are z fighting because they're currently both on the same plane. The plane and the triangle are both in the same distance from the camera, so we have some z fighting going on here. The shapes are overlapping. If I move you around, the shapes are overlapping. If I move you up or down, you are not overlapping. A little bit more of an interesting example would be if I were to go back to giving these test shapes a random z coordinate like this, and then we can actually move these shapes around in 3D space, and we will be able to see where the intersection starts and stops. So there's the plane, there's the triangle. We can see the triangle is currently wedged in the plane. The plane is fighting with the grid. I don't like that. That's annoying. I wish it wouldn't. If I were to move the plane up, or if I were to move the plane up or down, we can see that the overlap begins here and ends here. If I were to rotate the plane and move it backwards or forwards, we can see the intersection starts here on the sharp edge of the blunt edge of the arrowhead or whatever, and it ends here on the sharp edge. Okay, planes and triangles. So I am going to end this off here. Next time is going to be the big one. This is going to be triangles and triangles. That's going to be a bit much, so I'm just going to make that an entire video all on its own. After that comes raycast with triangles, and then it's time to start dealing with collision meshes, so actual collisions with 3D models instead of just primitive shapes. I know a number of you have expressed interest in doing collisions with terrain in GameMaker. And height maps are actually a bit of a separate thing, based on some assumptions that you may make about them, but that's a story for another day. So I'm going to stop now. If you want the code for this, look in the GitHub repository in the video description. I have a Patreon, so if you want to contribute towards these videos being made, I will definitely appreciate that. Links in all the usual places. You could see your name in the credits, hear yourself shouted out at the end, see a preview of my future plans, that sort of thing. Otherwise, I try to post about 2 game dev videos a week, one of these and one Let's Make a Tower Defense game. I hope you all enjoyed that, and I will see you all later. Special thanks to Edward Holt, Emily Koyo, Gunnar Clovis, Posho, Tusk, and Zenjamin for supporting these videos. If you want to see your name in the credits or hear yourself shouted out at the end, head on over to the Patreon page down in the video description to join the fun.